In this video, we'll be looking at the final section of the Further Mechanics booklet, Simple Harmonic Systems. Now this takes our idea of simple harmonic motion from the previous session and now applies it to some specific scenarios. So everything covered so far in the previous video is still applicable. But what we do is we look specifically at two certain examples that are very practical oriented and linked to practicals that you're expected to do. The first of which is a mass on a spring. So the mass spring system is simply a mass in a fixed position attached to a spring, vertically, horizontally, doesn't matter. And by displacing it, it will move in oscillation, a simple harmonic motion, continuously experiencing, as we expect, a restorative force pulling it back to its original equilibrium position. Now, whilst we can do displacement, acceleration, and so forth from our previous equations, we are given specific equations linked to time period for these two experiments. So for this one, time period is measured as 2 pi root m over k. Now, t being our time period is in seconds as standard. Nothing special there. Whereas m is our mass in kilograms, again, normal. K is the feature you might forget. As this is a spring system, K is the spring constant, as you've encountered previously with Hooke's law in the mechanics and materials section. So in newtons per kilogram. Now it's worth remembering, with these experiments, it is incredibly hard to measure the time period during the oscillation. It happens incredibly quickly. So normally, experimentally, you would measure roughly 20 oscillations at once to find 20 times the time period. So in doing repeat readings of 20 oscillations, you should find an average from which you can find an average of a single oscillation. Now that still occurs with this second experiment, the simple pendulum. So this only works under small angles, so approximately 10 degrees. If you go for a larger angle, in reality, you end up with a wobbling system, so energy being lost, and an imperfect oscillation. So in order to get simple harmonic motion, it must be a very small angle. Now, this again is a very simple equation structure of t equals 2 pi root. The difference is what's rooted, and this time it's L over G. So L is the length of the pendulum itself. Now it's important to know what that actually means. It is not the length of the string or the rod. It is the length from where that rod or string connects to the fixed position to the center of the mass, as it's labeled as bob here. So that center of mass is the point that we measure from, and it is vital that you don't miss that. G, as ever, is the gravitational field strength. So as it's given in your data sheet. Nothing particularly special there. You already know how to use that. 9.81 in newtons per kilogram or meters per second squared. Same thing. Now, with systems, we also have to consider the idea of resonance. Now, this ties in a bit with the waves topic, but we know that under ideal conditions, we can approach things like resonance quite easily. So remember, ideal conditions are where you have no external interaction, no forces or anything else affecting your system. It is isolated. So if we displace a mass on a spring, as we saw on the previous page, it will oscillate forever without any reason to stop at its resonant frequency. So the resonant frequency is unique per material, and it represents its maximum oscillation, so a maximum amplitude. So this would be considered free vibration, in which no energy is lost, no energy is gained, nothing changing force-wise, so it remains forever in this perfect simple harmonic motion. This obviously isn't realistic, but it's an ideal state and therefore works very well for models. Now, the more realistic aspect is that we know various forces, such as friction, for example, might cause energy to be lost. So instead, to maintain this perfect oscillation in the system, we would have to provide a force. So this driving force leads to what's called forced vibration. So this is where we can maintain oscillation of a system at its resonant frequency. And this can be maintained as long as you can provide that driving force and maintain it to match the resonant frequency. Because if it falls out of phase, the whole system will collapse, the wave function will go. Now, resonance isn't always an ideal thing. We don't always want it. It can happen randomly with things like wires that hold bridges, screws in planes, things that can vibrate under effects of things like wind. And that can be devastating to the structure. So instead, what we introduce is damping. Now, this is a way of reducing the energy in the system. So you're reducing the amplitude of the oscillation in various different ways. So you're draining energy from what is there. Now, there are 4 specific ways that you need to know how this happens. And graphically, you need to be able to represent them. So, first off, we have light damping. Now, light damping is a very gradual effect. And as you can see on these graphs, we're just representing from maxima, positive and negative. And in this case, you can see the maxima gradually drop, you go down, giving you a nice and simple funneling sort of effect here. Whereas with heavy damping, this happens far more rapidly, almost exponentially. So we can show that by following the peaks and following the troughs to show that narrowing effect. So you can see here, as I said, a funneling effect, narrowing as it goes along. Whereas for heavy, it does it more rapidly, almost exponentially on each side. Now they're very similar, very easy to compare, very easy to discuss. And that's the idea of some resistant forces or some external influence, maybe the material it's been placed in, so a different medium that's got slightly more density. But critical damping just stops the thing, pulls it back to the origin and causes it to stay there. So the current oscillation continues until a stationary point is reached in equilibrium and nothing else happens. So you're actually stopping the oscillation rather than allowing it to gradually fade. Overdamping takes this even further by preventing even the first section of the oscillation to complete and just holds the object in place and allows it very gradually to return to its origin. So you need to know these and be able to identify and sketch them in the exam. Now it's also worth noting that damping will have an overall effect on the resonant frequency of a material. So the frequency that is natural for that material, that it should resonate at, is not going to be fixed, as damping will reduce the frequency at which this maximum is reached. So this graph at the bottom here shows the peaks shifting to the left as damping increases. So this trend that we can see is very easy to recognize and also links to further topics later on where similar effects can be seen. So make sure you can pick it out in multiple choice. Thank you for your time.